In this video, we're going to focus on looking at isomorphic groups. What I mean by isomorphic groups is two groups that have the same underlying mathematical structure. The labeling might be different and names might be different, but they're behaving in exactly the same way, and ultimately all that's different is the way we've labeled the elements. I'm going to start by looking at some groups that we looked at in video 3 of the group theory videos. So if you're rusty on those or you haven't seen it, I'd recommend you probably have a look at that first to make sure you're happy with the ideas. So we've got the group on the left, the symmetries of an equilateral triangle. That's looking at a triangle and thinking all the symmetries. So we've got our do nothing symmetry, which is our identity element. We've got two rotational symmetries, rotating by 120 degrees and rotating by 240 degrees, which are our R1 and R2. And then we've got our three reflective symmetries, S1, S2, and S3, which are reflecting in our three lines of symmetry of our equilateral triangle. Then we're looking at composing these. So what happens if we do a rotation followed by reflection and so on. And that's how we're getting our Cayley table on the left here. The other group we're looking at, the permutations of three elements, is saying, let's imagine that we have elements 1, 2, 3. How might we rearrange these? Well, we might do nothing. We might just keep it as 1, 2, 3. That's our identity. Or we might do something where it becomes 2, 3, 1, for example, and rearrange those in those different ways. In total, there's 6 different ways, and I'm labeling those 6 different ways E, P, Q, U, V, and W. What I want to notice, and what we noticed at the end of the Group Theory 3 video, was that really, if I just take my group on my right and just relabel the element P as R1, relabel the element Q as R2, and so on, S1, S2, S3, and if I was to go through the Cayley table and do that all the way through the Cayley table, replacing all my that should be an R. Replacing all my P's with R1, replacing all my U's with S1, then it would become exactly the same as the group on the left. The only difference is here the letters I've chosen to represent this. So mathematically, the underlying structure is identical. It's purely the superficial labeling that changes here. So we're going to use this to say that these two groups are isomorphic. One thing worth noting straight off the bat here is that the way we've done our relabeling, so if we look at the order of S1 in the first group, S1 composed with S1 is E, so S1 has order 2, and U composed with U in the second group is E, so U has order 2. Whenever we're doing this, it must be the case that the order of the element is the same in both groups, otherwise relabeling is going to change the group there. We're not going to be able to have a complete matchup. So if we don't have orders matching between groups, we know we can't have an isomorphism straight away. Being able to match the orders isn't actually a guarantee that an isomorphism exists, but it's a good check. In most cases, it's going to be a way of finding out two groups aren't isomorphic if we don't have those matching up. So what I want to look at is how we can find some isomorphisms here. So I'm going to just go down and look at these two groups and see if we can spot an isomorphism between these two groups. This is a nice special case, but it's a special case that comes up a lot. So group G here, we've got the elements 0, 1, 2, 3, and we're doing addition modulo 4. The claim I'm going to make, and that you want to get quicker spotting this is going to be a cyclic group. 1 is a generator for all these other elements. If we just keep adding 1, if we start with 1 and just keep adding 1, we're going to get to the other elements. We're going to do 1 plus 1 is 2. We're going to get and add 1 again. We'll get 3. We'll add 1 again. And we'll get 0, which is our identity. Because we know if we add 0, then it doesn't change it. So seeing 0 as identity should be nice. So G is the group generated by the element 1. It's actually also generated by 3. You'll always have a case of a cyclic group that if you have it generated by one element, there will be another element that could have generated it. Because if you do 3 plus 3, you get 9, which is 1 modulo 4. If you do 3 plus 3, you get 6, which is 2 modulo 4. Add 3 again, you get 5, which is 1 modulo 4. Add 3 again, you get 0. So we could have said it was the group generated by 3, but we just need one generator here. If we look at H, so this is the group consisting of the elements 1, -1, I, and -I on the multiplication. I would recommend you pause the video for 30 seconds and see if you can find the generator. There's 2 possible answers. Well done if you did pause and find the generator. If not, just follow through with what I'm saying and make sure you're happy with it. The 2 possible answers here are I and negative I. Let's look at why we know the other ones couldn't be answered in the first place. 1 is definitely the identity. Multiplying by 1 doesn't change it, so that can't generate the group. If we start with 1, we'll only end up with 1. But and negative 1 squared, negative 1 times negative 1 is 1. So negative 1 has order 2. Not order 4, not the order of the group, so it can't be a generator. But if we start with I, then I squared is negative 1, times by I cubed is negative I to the 4 is 1. So I has order 4, and I generates all the elements in our group. So this is the group generated by I, and that's the notation we can use. Now, once we've got that, if we're trying to look for an isomorphism between these and our elements of G and H, then the identities must match up. So my identity of G is 0, my identity of H is 1. So there must be a mapping between those. And then 1, the generator of G, I'm going to match up with the generator of H here, which is I. And then if we do 1 plus 1 in G, we get 2. I'm going to match up with that if I do I times I in H, which gives me negative 1, and then plus 1 again. Well, there's only one element I've got left anyway, so that's a bit of a giveaway. 3 is going to match up with negative I here. So whenever we have a cyclic group, it should actually be really nice and easy to form, to find isomorphisms and find the mapping here. We just want to find a generator, and then if we've got one group, which we can write as our identity, and then G squared, G cubed, all the way up to G to the n minus 1, if we have n elements. And then we have another group with a generator H, so maybe H squared, all the way up to H to the n minus 1. Then straight away we know we can make, I'm going to label these E2 and E1, just they might be different identities. But straight away we can just do a mapping between those to get an isomorphism. So looking for a generator makes it really easy to find isomorphisms. Okay, what about cases where there's not an isomorphism? How can we go about arguing this? So let's look at this example asking us to show that this group consisting of all the odd numbers from 1 to 15 under multiplication modulo 16 is not isomorphic to the symmetries of a square. There's generally 2 good ways of showing 2 groups aren't isomorphic. One way is if the operation of one of our groups is commutative, so we'll have an abelian group, and the one of the other one isn't commutative, we won't have an abelian group, then we know we can't have an isomorphism. We could go this way, but you'd have to go through some work to check carefully whether your symmetries of your square form an abelian group or not. If they don't, you're sorted, because definitely multiplication will be. But the other way is probably the way I generally recommend if you haven't done work already, which is check the orders of the elements and see whether there's a chance of matching them up here. So looking at the orders of our elements of this first group under multiplication modulo 16, the order of 1, well, 1's our identity element, so the order of 1 is just 1, because 1 multiplied by 1 is 1, 1 multiplied by anything, 1 multiplied by x is x, so 1's our identity. The order of 3, well, if we do 3 times 3, we get 9, definitely no 1 modulo 16, multiplied by 3 again, we get 27, which is 11 mod 16, but if you multiply by 3 again, you do get 1 modulo 16, so the order of 3 is 4, because we need to do 3 to the power of 4 to get back to our identity element. Similarly, and you'll have to take my word unless you want to pause and go through it, but for 5 squared gives us 25, 5 cubed gives 125, still no 1 modulo 16, but 5 to the 4 should give us 1 mod 16. So 5 has order 4, whereas 7, if we do 7 squared, we get 49, which is 1 mod 16. So 7's a self-inverse as order 2, and then keep on going then. So 9, 81. 9 squared is 81, which is 1 mod 16. So the order of 9 is 2. The order of 11 is 4. The order of 13 is 4. And the order of 15 is just 2. So if we look at the elements of our symmetries of our square and we don't have 3 elements of order 2, 4 elements of order 4, then we know immediately that these two groups can't be isomorphic. So let's think about the symmetries of our square here. Well, we're going to have the do nothing thing, which is going to be our identity, which will have order 1. That's not going to be that informative. But what will we have order 2? Well, we'll have a reflection horizontally. We'll have a reflection vertically. We'll have a reflection diagonally this way. We'll have a reflection diagonally that way. And we'll have the rotation of 180 degrees. We'll also have order 2. So we've got 4 reflective symmetries and rotation by 180 degrees all have order 2. So we have 5 elements have order 2. Let's note this is definitely more. This only had 3 elements of order 2. So the groups cannot be isomorphic here. Obviously, I'll make sure I wrote a full conclusion in a paper. So what groups might come up? What groups you need to be aware of? So groups of order 2, there's only one possible group of order 2, and that's your identity and the self-inverse there. Group of order 3, there's only one, is a cyclic group. For any order, you can always have a cyclic group, so that's a given. Groups of order 4, you can either have your cyclic group, or you can have one where you've got the Klein 4 group, where all the elements are self-inverses. So that's a special case, and it's worth knowing that you can get 2 different groups of order 4. Order 5, you can only have cyclic. And order 6, you can either have your cyclic group of order 6, or scrolling all the way back up, you can have this group here, which is symmetries of an equilateral triangle, sometimes written as S3. You don't need to know the name of it, but it's worth knowing that you can have a non-cyclic group of order 6. Order 7, again, you can only have cyclic. By the time you get up to 8 elements, there's a few different groups. You don't need to know them all, but you can have a few different groups of order 8 by that point. Thank you very much.